Hello everyone, welcome back again to my young tutorials. In this video we're going to tackle about chapter 10, heat transfer by convection. Heat transfer by convection is the mode of energy transfer between a solid surface and the adjacent liquid or gas that is in motion. It involves the combined effects of conduction and fluid motion. There are two main types of convection, which is the forced and the natural convection. Forced convection with the help of external means, and by natural convection it is caused by the buoyancy forces. So one example of this is the cooling of boiled egg by forced and natural convection. So for more understanding, let's solve problem regarding with the heat transfer by convection. Example number 1. Consider the following, or consider the flow of a gas with density 1 kg per cubic meter and a viscosity of 1.5 times 10 raised to negative 5 kg over meter second and specific heat of 846 joule per kilogram degree Kelvin and the thermal conductivity of 0.01665 watts per minute degree Kelvin in a pipe of diameter 0.01 meter and a length of 1 meter, and assume the viscosity does not change with the temperature. The Nusselt number is given by L over D ratio greater than 10 and Reynolds number greater than 20,000 is given by the Nusselt number is equal to 0.026 Reynolds raised to 0.8 multiplied by the Prandtl over 1/3. While the Nusselt number of a laminar flow for Reynolds number less than 2100 and the Raynaud-Prandtl D over L is less than 10 is given by Nusselt number is equal to 1.86 multiplied by the Reynolds-Prandtl D L raised to 1/3. So find the heat transfer coefficient if the gas flows through the pipe have an average velocity of 0.1 meter per second. So solution, we need to first solve the Reynolds number. So given that this equation, Reynolds is equal to dV rho over mu. We have the diameter of 0.01 as given here, multiplied by 0.1 as our velocity, times our density, which is 1 kg per cubic meter, over mu, which is also given as 1.5 times 10 raised to negative 5, which is also our viscosity, and we get the Reynolds number 66.7, or by rounding this off we get 67. And the Prandtl, we need to solve first the Prandtl. Cp for the specific heat times the viscosity over the thermal conductivity. We have the Cp, which is 846 multiplied by 1.5 times 10 raised to negative 5 as our viscosity over the thermal conductivity of 0.01665, and we get the Prandtl of 0.76. By the relationship between Prandtl and the Reynolds number D over L is given by 66.7 as our Reynolds number multiplied by 0.76 as our Prandtl number multiplied by the diameter, which is 0.01 over the length, which is 1, and we get 0.507. And to relationship between the Reynolds number and Prandtl into the Nusselt number, we use the Nusselt number for a laminar flow, which is given 1.86 multiplied by the Reynolds brands multiplied by the diameter over the length raised to 1/3. By plugging this, what we have and what we solved to the Nusselt number 1.86 multiplied by 0.507 raised to 1/3 is equal to 1.483 as our Nusselt number for a laminar flow. So since we need to find the heat transfer coefficient, we need to use this equation. Nusselt number is equal to heat transfer multiplied by the diameter over the thermal conductivity, or we can rearrange this equation into this equation as a heat transfer equal to the Nusselt number multiplied by our thermal conductivity over the diameter. And we have, by plugging these values, the values that we have here into this equation, we have 1.483 multiplied by 0.01665 as our thermal conductivity over the diameter of 0.01, and we get the heat transfer coefficient of the gas flow through the pipe of 2.47 watts over watts per square meter degree Kelvin.